paste. And all of those examples will be connected to class number 1. Okay, that's going to be my data set. And apart from that, I'll build up more. I'll have like a sinusoidal function here on top of some sequence from 0 to, could be from 0 to 1000 maybe. No, 0 to 9, whose length is going to be 1000. No, 1025, I think it's going to be better. That's something to explain after. Because this is just a sinusoidal function, as you guys can see. But instead of using a sinusoidal function, I could embed it in some space, like this. If I embed it, I could have 2 dimensions like this. And I think this will be more interesting to see what's happening. Sorry? Oh yeah, there's a plot inside. Of course. So you see I have some sort of a shape like this, and that's the shape I'm interested. Why I'm interested in that shape? Just because I can now bind along the rows of my data set that shape and say that this is going to be connected to another class, to class 2, for example. And if I now plot, let me see if I can plot this, if data is correct. No, data is not correct. Okay, so I should somehow, let me see, I have to say how many dimensions I have here. This is going to be, let me see how many examples I have here. The number of rows I have here. 1000, yeah, perfect. That turns out to be perfect. 1000 twos here. There is something missing. Oh yeah, there's another parenthesis here missing. No, it's not good again. Okay, let me see data. Okay, data is okay. Let me use just the first 1000 dimensions. It was 1000 rows, sorry, because I added up wrong dimensions here. Wrong dimensions. Okay, maybe if I do this, if I see bind, let me do by parts. I'm gonna do this before just to see if it works, and then I do the next step. Yeah, it's working now. Okay, sorry, but when you do things on the fly, things happen. So I'm gonna plot. Yeah, of course. I'm interested in plotting this. I'm use the last column as a color. So the color is gonna be the last column, the third column. As you guys can see, I have this space. So if I have this space, in your opinion, how many linear hyperplanes, or how many hyperplanes, because every hyperplane is linear, how many hyperplanes should I use if I had, for example, a multi-layer perceptron? I should have, like, for example, one hyperplane here, cutting here, for example. Another could be here, right? Another hyperplane could be here, somehow here. And another hyperplane could be here. Okay? So I should have at least like 4 hyperplanes. Maybe you may claim that with 3 is possible, but with 3 you're going to have more error. I think 4 is nice. So in this is a 2-dimensional space. What's the shuttering coefficient for a 2-dimensional space? It is here. The shuttering coefficient is here. If I plot, it is this function. And what's this function? This function is exactly in here. These are the terms for that function. Not here, but here, the coefficients. So in that situation, I have approximately 1 times the number of samples I have to the squared, because it's a times n to the squared, plus a b times n plus a c. What's going to be a in this situation? It's like 1.008. What's b? Minus 1. I'm gonna call like 1.25, 1.75 just. And c is 4.26 approximately. Okay, so I'm going to save this guy, and this is our, I'm going to get back to R, and this is our shattering coefficient for a single neuron in R2. Ah, there's no n. Okay, let's say we have a sample that varies from 1 to, could be 1,000. So now I can compute the shattering. The shattering for R3 is different. Do you guys remember what's the shattering for R3? I just don't. It's here, right? Somehow here, R3 coefficients. So it's like 0.19 n to the third plus 1 times approximately n to the square minus 8 times n plus 14. So that's my second shattering coefficient, copy. Okay, that's my second shattering coefficient. If I plot both, I will see an amazing difference, right? Let's plot the shattering coefficient for R3 before. This is, oh no, not here, but here, I believe. Oh yeah, here. And now we have for R2, I'm going to plot using lines and using a different color, maybe red, to make it easier to see. It's just impossible to see the other. It's so below, yeah? But maybe if I plot just R2, we can see it. Okay, better to see now, right? So what I'm going to do now, if I am using the multi-layer perceptron with 4 hyperplanes, what's going to be my shattering coefficient? That's the question. It's going to be a combination of 4 hyperplanes in R2. So it's going to be the combination of 4 hyperplanes in R2. This is going to be the complexity. So if I somehow decide to use a multi-layer perceptron with 4 hyperplanes in R2 using 4 hyperplanes, that's my shattering. So now if I plot that shattering, to you, you guys can see the complexity. And I could say, okay, let's plot the shattering for R3. Because just to compare, just to see what happens with R3 with a different color. Oh, the complexity with 4 hyperplanes is amazing. It's huge. And the question that stays is it possible to use just a single hyperplane to shatter this space? This original space? Is it possible to use just one hyperplane? In this space is impossible. But if I apply a second order polynomial kernel, what's a second order polynomial kernel? It's the same as getting this data and saying that the first dimension of that data set is going to be to the square. And I'm going to bind that. The second dimension will be the square root of 2 times the first dimension times the second dimension. I can show the proof after in another lecture probably. And this is the second dimension to the square. This is exactly what a second order polynomial kernel does in some space. And I'm gonna keep the last dimension just because I want you guys to see the colors. And this is a second order polynomial kernel. That's the effect of a second order polynomial kernel. Now if I plot it using a 3D plot, second order polynomial kernel from the first to the third dimension, and using the color as the last dimension, which is the fourth now, you guys can see that with a single hyperplane I can divide the space. So what's the best situation? Should I use this space with a single hyperplane, or should I use the other space with 4 hyperplane? Of course, this space, because the complexity of the shattering is smaller. And what that means basically is this. If the complexity is smaller, what should I do now? Should I do this next step? So here, I believe we computed the complexities, right? Let me remember. Yes, this is the complexity for the multilayer perceptron. And the complexity for the shattering coefficient in what it is? Yeah, here for the one single hyperplane R3 is this guy, right? So how can I compare the minimal sample size to understand when I can ensure learning? That comes from the rightmost term from that last inequation, last bound we saw. I think you guys remember, it's here, it's like 2 times m times the exponential value of something that's negative, right? It's this guy. And now I ask you, it's not gonna run, but I'm gonna enter here just to save it, okay? What's m? M is the shattering coefficient. So m for the multilayer perceptron with 4 hyperplanes in R2 is this. What's epsilon? Epsilon is the quantity, the divergence quantity we accept. If we say we're gonna accept like a divergence of 10% in between the empirical and the expected risk, it's like 0.1. If we accept 5% of difference, it's gonna be like 0.05. Let's say we're gonna accept like 0.05. This is providing an upper bound for the probability term for the multilayer perceptron in R2, again, with 4 hyperplanes. If I do the same, but now for a single hyperplane in R3, using the same parameterization, but this is the same as using a multilayer perceptron with a single hyperplane, but in R3. Do you agree? It's the same. It's exactly the same. Now if I plot both, let's plot this guy first, R2, so you guys can see what's happening. This is the result. We can actually, let me see. Yeah, that's the result. I hope it is. Let me close it. Yeah, it is. There's no guarantee until now, at least. Let's see the other. It's almost converging. It's getting back. It's starting the convergence. With what's the sample size? 1,000 examples. As you guys can see here, 1,000 examples. So if I have like a greater sample, let's say I have a sample with 10,000 examples. And again, I have to compute the shattering coefficient. Let's compute, because now it changed the sample size. So let's get back. Yeah, this is this for the single. This is for R2 and and that's gonna be for R3. Okay, so now we compute the shattering coefficient for the multilayer perceptron in R2, right, with 4 hyperplanes, and now we can finally compute the upper bounds. Oh yeah, they're here. The upper bound we have for the multilayer perceptron in R2 with 4 hyperplanes, and the upper bound we have, let's get back. You guys scream if I find it, because maybe I lose it. Is it? No? 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 Where is it? No, it's not there. Maybe if I do this, the probability of upper bound MLP in R3. one hyperplane is equal, yeah, it's here. Okay, so now I can plot. If I plot first this guy with a single hyperplane in R3, there is a perfect convergence. If afterwards, yeah, I know that feeling. If I plot the other guy in R2 with 4 hyperplanes, it's also converged somehow. But let's plot both together. Let's plot using lines and a different color, maybe red here. It's almost impossible to see, so we better do this. We better stay in the y range in between 0 and 1, because this is an upper limit for probability. It doesn't matter, it doesn't mind the values which are greater than 1. They are not necessary, they're not even necessary, right? And now I'm going to plot for a single hyperplane. Take a look. For a single hyperplane, it converged. But actually, for 4 hyperplanes, it didn't. We should increase the sample size. Okay, so let's increase the sample size. So now I'm going to consider a sample with 1 additional 0. And now I will compute this guy. Let's get back. This shattering for R2, the shattering for R3, now it's easier, the shattering for R3, the shattering coefficient for the multilayer perceptron. Is it? No, it's not this guy, it's this guy with 4 hyperplanes, and then the upper bounds, and then this upper bound for the multilayer perceptron, and the upper bound for the where is it? Yeah, a single hyperplane in R3. It's also the multilayer perceptron, but in a different space with more dimensions. Okay, so now we plot. We finally plot. Okay, plotting. It's converging, but let's see for the other. It's also converging. And what this point tells me is basically the minimal sample size I need to ensure convergence. That tells me, that proves me mathematically and probabilistically the minimal sample size I need to ensure learning. I need to ensure at most a divergence of 0.05 in between the empirical and the expected risks, in between the risk I have in a sample and the risk I will have in the real world conditions. If I decide to use the multilayer perceptron on R2 with 4 hyperplanes or on R3 with a single hyperplane. And if I decide, okay, I see here that with 2 times, okay, to the 4th, so maybe I could consider like a smaller sample size here, like that, because we can better plot if we do that. So I'm going to run again just to see. So this is R2, this is going to be R3, this is going to be the shattering coefficient for the multilayer perceptron in R2 with 4 hyperplanes, and the upper bounds. The first upper bound, the second upper bound is here, and now plotting finally to see the results. So what you can conclude is that if I decide to use the same technique, the same multilayer perceptron, with a single hyperplane in R3, with a little more than 5,000 examples, I ensure the convergence for this scenario, having at most a divergence of 5% in between the expected and the expected and the empirical risk, the risk in a sample. And if I decide to use the other space, I need more than 15,000 examples. So this means I have more complexity for this multilayer perceptron instance. This basically means I have more functions in this space. It is capable of building up more complex classifiers. And this is capable of building up simpler, but enough in this case. classifiers. Enough just because I had this. Where is the space? It's not here. It's here. Because here I have this ability with a single hyperplane to shatter the space. So now, you know what's the most important thing I would like to keep in your minds now? What's more important? It's the algorithm or it's the space? It's always the space. It's always the space. The algorithm, it doesn't matter. Actually, it matters because I can use support vector machines, and there's no better algorithm in the literature just because the support vector machines finds the best hyperplane position in terms of this distance I'm showing there. So it's going to shatter in this place, exactly in the middle. And why is that the best place? Just because if I have some noise, the noise is going to propagate, but it's going to have some room to propagate. So when we use something like deep learning, what is deep learning doing? That's a question that I also leave for you guys. Deep learning is building up a kernel. Building up some kernel. Building up some sort of kernel on top of which the classification process is performed. Okay. Now we have a way of estimating the shattering coefficient. I'm going to share the code so you guys can run if you want, if you wish. So now we have an estimation here for any kind of hyperplane. So if you want to consider 2, 3, 4, or 5 hyperplanes, you have to power to that number. You have to compute for a single hyperplane, and as you have a composition of 2, 3, and 4 hyperplanes, you are multiplying hyperplanes, in fact. You are multiplying functions, in fact. So you are multiplying complexities. That's why we have a power, a function powered to 2, to 4, to 3, to something, if we decide to use more hyperplanes. Okay? I think this is quite interesting. Very, very interesting, in my opinion. Because now you guys can see that it's much more important to understand space you are working on than just guess the number of hyperplanes you decide to use. And now you also have a bound, a way of computing an upper bound and ensuring a minimal sample size to guarantee learning, to say you are indeed learning. After that, in the next Friday, I thought that we could open up the last formulation we were doing here, because if we open up that, we find the generalization bound. The generalization bound, people may call it like empirical, structural, what's the name? I forgot. Structural risk. Structural risk. It's also a name for that. But from that generalization bound, we can derive the Tikhonov regularization, the random marker complexity, POC learning, and also the large margin bounds. But that's not the most important. In my opinion, the most important is to find the generalization bound, because after that, you have a practical way of performing experiments, of ensuring that after some minimal sample size, you are sure your result is good.